Pause for a moment and consider the arithmetic we all take for granted. 100 billion galaxies, each a swirling island of 100 billion suns with trillions upon trillions of worlds circling them. It feels mathematically certain, doesn't it? A cosmic lottery with that many tickets. Surely someone else must have won. It's the most logical, comforting conclusion a mind can reach, and I am here to tell you with the cold clarity of a pencil and paper that this logic is a beautiful, seductive lie. Not because I'm a pessimist, but because I finally sat down and did the math without letting hope hold the pencil. When you do that, when you banish wishful thinking from the equation, you find yourself in a room that is utterly silent, and you are the only one breathing. For years, I've wrestled with this, debating biologists who see life's tenacity, astronomers who see infinite real estate, and engineers who see possibility. They all start from the same place. Richard, the numbers are just too vast. You cannot argue with 1 trillion planets. And my response is always the same. Yes, you can, because the numbers on the other side of the ledger, the numbers representing the hurdles, are just as vast. No one wants to look at those. Let's be precise. I'm not talking about microbial slime. Perhaps that's common, a film of primitive life on 1 billion ocean moons. Chemistry is messy. It tends to make complex molecules, and sometimes those molecules start shuffling and copying. Fine. I'm talking about the kind of life that builds a city, that wonders about its own origin, that points a telescope at the sky and asks, who else is out there? Conscious technological life. The reason everyone assumes it must be common is simple: the sheer scale of existence. It feels wasteful, even arrogant, to think all of this was built for a single audience. Let's walk through the logic, because on the surface, it's compelling. Start with our own galactic backyard, the Milky Way. Roughly 200 billion stars. We now know, thanks to missions like Kepler, that planets aren't the exception. They're the rule. Most stars have them. So in this galaxy alone, we're talking about hundreds of billions of worlds, 1 trillion if you count the small, cold ones. A certain fraction of these reside in what we clumsily call the habitable zone, that Goldilocks region, not too hot, not too cold, where liquid water could potentially exist on the surface. Now, habitable zone is a dangerously misleading term. It conjures images of forests and oceans. It should be called the liquid water possible zone. That's all it guarantees. Mars is in this zone. It's a frozen, radiation-blasted desert. Venus was likely in this zone once. Today, its surface is hot enough to melt lead, and it rains sulfuric acid. So, habitable does not mean inhabited. But even with a conservative estimate, we're left with tens of billions of these not impossible for water worlds in the Milky Way alone. Multiply that by the 100 billion other galaxies, and you get a number that is essentially meaningless, something like 10 to the 22nd power, 10,000 billion planets that aren't obviously hostile to life as we know it. And this is where most people stop. They see that colossal number and declare the case closed. If you had 10,000 billion lottery tickets and only one winner, you'd bet your life that someone somewhere is holding it. The odds demand it. But here is the catastrophic flaw in that thinking. A potentially habitable planet is not the same thing as a planet with life. A planet with life is not the same thing as a planet with intelligence, and intelligence is not the same thing as technology. And technology is not the same thing as a civilization broadcasting signals at the exact moment we happen to be listening. Each of these transitions is a filter, and we have absolutely no idea how fine the mesh of these filters is. This is the part everyone skips. They get high on the massive initial number and forget they have to divide it by a series of unknown, potentially astronomical figures. There's a famous framework for this devised by Frank Drake in the early 60s. It's not a physical law, but more of an inventory of our ignorance. You start with the rate of star formation, multiply by the fraction of stars with planets, then by the number of habitable worlds per system. So far, so good. We have decent data. But then comes the gauntlet. You multiply by the fraction of those worlds where life actually emerges, then by the fraction where that life evolves into something intelligent. then by the fraction that develops detectable technology, and finally, you multiply by the length of time such a civilization broadcasts its presence. It's a beautiful structure built on a foundation of pure guesswork. The first 3 terms we can estimate. The last 4, we are staring into a void. We have a sample size of 1, Earth, to guess at probabilities that could be 1 in 10 or 1 in 10 billion. The equation doesn't give you an answer. It gives you a receipt for everything you don't know, and what you don't know is almost everything. The final term is particularly cruel, the lifespan of a technological civilization. If we burn bright for a few centuries and then snuff ourselves out, then even if millions of civilizations have risen and fallen, the chance that any 2 exist at the same cosmic moment is virtually 0. Ships passing in a night that is 13.8 billion years long. Let's drill down on that first most critical step, moving from a sterile, wet rock to a self-replicating life form. How hard is that? We know it happened here, and it happened fast. Geologically speaking, within a few 100 million years of the planet cooling down. This speed makes many people assume it's easy. Just mix chemistry, water, and time, and life bubbles up. Simple. But we have one data point. One, and that data point is catastrophically biased because if it hadn't happened, we wouldn't be here to count it. You cannot do statistics with a sample of 1, especially when your very existence is the result. That's not science. It's a conjuring trick. For all we know, the origin of life requires a chemical accident so rare it occurs on only 1 planet in a billion. If that's the case, then even with all those worlds, you'd expect life to have arisen exactly once in the observable universe. We'd be it. I'm not saying that's the number. I'm saying we don't know the number. And that is the core issue. People assume the probability is high because it feels like it should be high. They mistake a feeling for a calculation. Imagine you sit down at a poker table or dealt 5 cards and get a royal flush. You might exclaim, wow, this game is easy. Everyone must get these all the time. But you'd be wrong. The odds are 649,740 to 1 against. You just witnessed a miracle and assumed it was the norm. That's what we're doing with the origin of life. We've looked at one hand, saw a royal flush, and declared the game trivial. We haven't examined any other hands. We have a sample of 1. And this brings me to a deeper point. People often say, but we found amino acids on meteorites. The building blocks are everywhere. True, the bricks are everywhere. But a pile of bricks is not a cathedral. The gap between a drifting amino acid and a bacterium that can metabolize, reproduce, and evolve is not a small gap. It is a chasm so wide that despite decades of trying, we have not been able to build a single living cell from scratch in a lab. We don't fully understand how it happened the first time. We are like cavemen finding a smartphone and assuming it's just a shiny rock. All right. Let's be generous. Let's say I'm wrong about that first filter. Let's assume life does bubble up on 1 in every 10 habitable worlds. Now we have billions of living planets. Now we hit the second filter, and this one is brutal. Life existed on Earth for 3.5 billion years before anything you'd call intelligent showed up. 3.5 billion years. For the vast majority of Earth's history, the pinnacle of evolution was a single-celled organism floating in the primordial soup. Then complex cells appeared. Then after another billion years or so, multicellular life. Then finally, after another long stretch, a creature with a brain capable of abstract thought. So here is the billion-dollar question. Was that progression inevitable? Was it a cosmic conveyor belt where simple life inevitably leads to talking apes? Or was it an accident, a series of freakish 1 in a billion coincidences that just happened to line up here? The evidence painfully points to the accident. Consider the eukaryotic cell, the complex cell type that makes up every plant, animal, and fungus. It was born from a singular event that appears to have happened exactly once in 4 billion years. One simple bacterium swallowed another, and instead of digesting it, they formed a symbiotic partnership. The swallowed one became the mitochondria, the power plant of our cells. That event, as far as we can tell, happened one time. Not twice, not 100 times, once. Without that one-off accident, you never get complex life. No plants, no animals, no brains. And that's just one bottleneck. The evolution of sex, the Cambrian explosion, the development of the eye, each of these could be wildly improbable flukes. Think about intelligence itself. Evolution has no goal. It doesn't strive for smarter beings. It just selects for whatever works. Beetles are a monumental success story. Bacteria are even more successful. A big brain is a terrible evolutionary investment. It consumes 20% of your body's energy for only 2% of its mass. For most creatures, that energy is better spent on stronger claws, faster legs, or more offspring. Intelligence only became an asset under a bizarre and specific set of ecological pressures. Change a few details of African geology or climate a few million years ago, and we wouldn't be here. Dinosaurs ruled for 160 million years and never built a radio. If intelligence were the default destination, they would have gotten there long before us. The fact that they didn't tells you something profound. Intelligence is not the norm. It's a cosmic fluke. So the chain looks like this: a habitable world, the origin of life, the evolution of complex cells, the emergence of multicellularity, the development of nervous systems, the rise of intelligence, the invention of technology, and finally, a civilization broadcasting at the same time as another. If any one of these steps has a probability of, say, 1 in a billion, you've just divided that massive initial number by a billion and wiped out all your civilizations. If 2 or 3 of those steps are that unlikely, the expected number of intelligent species in the observable universe drops below 1. We are the lucky, or perhaps the only winner. Now I can hear someone objecting, "Oh, Feynman, you're just making up these probabilities. You're guessing." And you're right, I am guessing. But the optimists are also guessing. The difference is I'm being honest about the size of our ignorance. They are sweeping it under the rug, hiding it behind a curtain of "it must be so." Let's shift from biology to physics, because even if you grant me another civilization, the physics of contact is utterly mathematically devastating. Our nearest stellar neighbor, Proxima Centauri, is a little over 4 light years away. That sounds close in cosmic terms. But let's ground that. Light travels at 186,000 miles per second. In a year, it covers nearly 6 trillion miles. So 4 light years is about 25 trillion miles. The fastest object we've ever launched would take roughly 75,000 years to get there. That's not a journey. That's a geological epoch. The last ice age ended only 12,000 years ago. We're talking about a travel time 6 times longer than all of recorded human history, and that's to the closest star. Most stars are thousands of light years away. The galaxy is 100,000 light years across. The nearest big galaxy is 2 million light years distant. You want to visit them? You want them to visit us? Let's talk about the energy required. To push a spaceship the size of a car to even 10% of the speed of light requires the energy of 1,000 hydrogen bombs. And that just gets you to 10%. At that speed, the trip to Proxima takes 40 years. You need fuel to stop, which means more fuel to accelerate that fuel, and you are immediately trapped by the tyranny of the rocket equation. This isn't an engineering problem we can solve with better materials. It's a mathematical law. The fuel you need grows exponentially with the speed you want. To get a meaningful payload to another star in a human lifetime requires energy sources that are, as far as we can tell, beyond the realm of sane physics. Some propose light sails pushed by giant lasers, a brilliant concept that bypasses the rocket equation, but the engineering is a nightmare. To push a tiny probe to 20% of light speed, you'd need a laser array putting out more power than the entire planet currently generates, focused on a sail the size of a football field for minutes, aiming at a target accelerating away from you. Could it be done? In principle, maybe. Would any civilization bother? I'm deeply skeptical. And then there's the dust. Space isn't empty. At a fraction of light speed, a grain of sand hits your ship with the force of a bomb. A pebble would be catastrophic. And the interstellar medium is full of hydrogen atoms. At high speed, each atom becomes a tiny, damaging bullet. The radiation and erosion would be severe. More shielding means more mass, which brings the rocket equation back to laugh at you. Forget travel. What about just listening? SETI, the search for extraterrestrial intelligence, is a noble effort. Point radio telescopes at the sky and wait for a pattern. But the physics here is just as grim. Radio signals obey the inverse square law. The power you receive drops with the square of the distance. A signal from a star 10 light years away is 100 million billion times weaker than it was at the source. At 1,000 light years, it's virtually undetectable. For us to hear an omnidirectional broadcast from across the galaxy, the transmitter would need to output the entire energy of a star, turning a sun into a radio station. Even a Type 2 civilization would find that a bit excessive. And if they're beaming a focused signal, they have to be pointing it exactly at us. The cosmic coincidence required is staggering. And from other galaxies, forget it. The signals just vanish into the cosmic microwave background noise, swallowed by the relentless math of distance. But there is a problem even more devastating than distance. It's time. The universe is 13.8 billion years old. Our galaxy is almost as old. Some stars formed billions of years before our sun. If intelligence arises with any frequency, some civilizations should have had a 5 or 6 billion year head start. They should have spread across the galaxy by now. Even at a crawl, a single motivated species could colonize every star system in the Milky Way in a few tens of millions of years. That's a blink of an eye compared to cosmic time. They could have done it 1,000 times over by now. Their artifacts should be everywhere. Their signals should be inescapable. Their engineering projects, like Dyson spheres, should be visible to our telescopes. And yet, the sky is silent. The solar system shows no sign of anyone ever having been here. No probes, no mining operations, no monuments, just cold rock and empty space. This is the heart of the Fermi paradox. If they are out there, where are they? People have invented countless stories to explain this silence. Maybe they all destroy themselves. Maybe they are hiding. Maybe we live in a cosmic zoo and they're just watching us. Maybe they communicate via means we haven't discovered yet. Let's look at the self-destruction idea. It's the most plausible of the excuses. The concept is that every technological civilization inevitably invents something it can't control. Nuclear weapons, a gray goo nanotech disaster, an AI uprising, and wipes itself out. This is depressing, but it has a grim logic. We've had nukes for less than a century and have already come frighteningly close to using them. Give a species enough power but not enough wisdom and poof. But this explanation demands a 100% fatality rate, not 99%, 100, because if even one civilization in 1,000 survives its technological adolescence and begins to spread, they'd be everywhere by now. The self-destruction hypothesis requires that no species anywhere, ever, under any circumstances, figures out how to not blow itself up. That's a remarkably strong and pessimistic claim. The zoo hypothesis is even worse. It requires a galaxy-wide conspiracy of silence maintained by thousands of independent civilizations for millions of years. One rogue alien with a radio transmitter would ruin the whole thing. Conspiracies are hard enough to keep in a single high school, let alone across an entire galaxy for eons. It's not an explanation, it's a fairy tale. These are fun to think about, but as a physicist, I have to be honest with myself. Most of these are not explanations. They are stories we tell ourselves to preserve the comforting belief that we are not alone. They make no testable predictions. They don't connect to any known physics. They are just so stories. The simplest explanation, the one that requires the fewest assumptions, the one that is perfectly consistent with everything we observe, the empty sky, the silent radio, the sterile solar system, is this: technological intelligence is so mind-bogglingly rare that we are, for all practical purposes, utterly alone in the observable universe. Maybe not literally the only ones, but so isolated by space and time that the isolation is effectively absolute. And this brings me to something profound about physics itself. Physics doesn't care what we want to be true. That is its great virtue. It tells you what is, and what it tells us is that the universe was not designed for us. It wasn't designed at all. It's just a set of rules playing out. And those rules, under incredibly narrow and specific conditions, allow for brief flickering moments of organized complexity that can wonder about itself. Look at the checklist for a planet like ours. You need a star that isn't too violent. Most stars are red dwarfs, which make up 75% of the galaxy, and they are temperamental, blasting their close-orbiting planets with deadly flares. You need a planet in that narrow liquid water zone. You need a magnetic field to deflect stellar radiation. You need a large moon to stabilize its axis, preventing chaotic climate swings. You need gas giants further out to act as cosmic vacuum cleaners, sucking up deadly asteroids. You need plate tectonics to regulate the atmosphere. You need the right amount of radioactive material in the core to drive that tectonics. You need to avoid being tidally locked to your star. You need time, billions of years of uninterrupted, catastrophe-free time, no nearby supernovae, no gamma-ray bursts. Our sun is a remarkably calm, stable star. That's rare. Most of the cosmic real estate is ruled out by stellar physics alone. And all of that just gets you a stable platform. It doesn't even get you to the first step of biology. The universe is not friendly to complexity. The second law of thermodynamics is a constant grinding force pushing everything toward disorder, toward a featureless equilibrium. Life is a temporary local rebellion against entropy. It's a ripple on a pond powered by the flow of energy from a hot sun to cold space, and ripples don't last. They flatten out. Think of it this way. You drop a stone in a calm lake. For a few seconds, there is a beautiful, complex splash. Waves radiate, patterns form, and then it subsides. The lake returns to stillness. The lake doesn't care about the splash. It was flat before, and it will be flat after. The entire history of life on Earth, all 4 billion years of it, is that splash. We are a brief, beautiful agitation in an ocean of entropy, and the second law guarantees that the agitation will end, not might end, will end. Stars burn out, galaxies wind down. The universe marches relentlessly toward a cold, dark, featureless end. We exist in a narrow window of time between the fiery birth of the cosmos and its slow, cold death. On one particular rock around one particular star, chemistry did something unusual. And that unusual thing produced creatures who could look up and ask if anyone else was looking back. The physics says probably not. And you know what? I don't find that depressing. I find it astonishing. If we are the only ones, if this is the sole place in all that unimaginable vastness where the universe has woken up and looked at itself, then what we have here is not ordinary. It is not a statistical inevitability. It is a freak event of such staggering improbability that it borders on the miraculous. Not a supernatural miracle, but a mathematical one. Something so unlikely that it demands our absolute attention and respect. When I look at the night sky, I don't feel small. Some people say they do. I feel lucky, unreasonably, absurdly, cosmically lucky, because the same physics that lights the stars also lights the neurons in my brain that can marvel at them. And as far as we can tell, that trick, that magnificent trick of matter waking up and looking around, has happened exactly once. I'm not arguing we should stop searching. We absolutely should not. Searching is vital precisely because the answer matters so much. Finding another example would revolutionize biology, physics, philosophy. It would be the single greatest discovery in human history. But we have to be honest about what we've found so far. Decades of searching, thousands of star systems examined, and nothing, no signal, no artifact, no anomaly that requires an intelligent explanation. Every promising lead has turned out to be a natural phenomenon or our own interference. That doesn't prove we're alone, but it's starting to be a lot of absence. And at some point, a lot of absence starts to look like evidence. If I searched every room in your house and didn't find an elephant, I'd be fairly confident there's no elephant. We haven't searched every room in the cosmic house, not by a long shot, but we've searched enough that the idea of a universe teeming with obvious loud civilizations is getting harder and harder to defend. Some say we're looking for the wrong thing, neutrinos, gravity waves, something exotic. But that argument cuts both ways. If their communication method is invisible to us, then for all practical purposes, they don't exist from our perspective. Invisible is as good as absent. Others say we haven't been listening long enough. True, We've only been seriously listening for a few decades. The galaxy is vast. Maybe the signal is on a frequency we haven't checked. I accept that. But our technology is improving exponentially. And every decade, the result is the same: silence. At what point does the accumulation of silence become a data point? There's a philosophical trap here. Every time we fail to find evidence, the hypothesis for alien life gets more baroque. They're hiding. They're too advanced. They've transcended physical form. They're made of dark matter. Each modification makes the theory more unfalsifiable, more like theology. A theory that can explain every failure explains nothing. If your model has been patched 17 times to account for 17 failures of detection, maybe the simpler model is the right one. They aren't there. I know this is uncomfortable. We are social creatures. The thought of being utterly alone in the cosmos is deeply unsettling. It feels wrong. It feels cold. It feels like the universe should have more to it than one fragile species on one small planet. But feels wrong has never been a reliable guide to physics. Quantum mechanics feels wrong. Relativity feels wrong. The fact that time slows down when you move fast feels wrong. All of it is true. So maybe being alone is the same kind of bitter truth. Maybe the universe really is as silent and empty as it looks. And if that is the case, then what follows? What is the consequence? The consequence is that this, right here, right now, matters more than we can possibly imagine. What happens on this planet in these few millennia matters in a way that nothing else in the universe can, because there is no one else to carry the torch. No one else will discover quantum gravity. No one else will compose a symphony like Beethoven's. No one else will look at the night sky and feel that unique human blend of awe and terror. Think about what we have accomplished in a mere 10,000 years of civilization. We went from scratching marks on clay to deciphering the structure of the atom. We decoded the laws of motion, of electromagnetism, of thermodynamics, of quantum mechanics. We figured out that the stars are other suns, that our galaxy is one of billions, that the universe began in an unimaginably hot, dense state. A species of clever primates on a small rock worked all of this out using nothing but their brains and some clever instruments. That is either the most ordinary thing in the universe or the most extraordinary. And every piece of evidence we have points to extraordinary. If we wreck this, if we burn this planet to a cinder, if we blow each other up or just let ourselves slide into apathy and ignorance, it's not like the universe has a backup copy. There is no second draft. There is no other civilization down the road that will pick up where we left off. The experiment of intelligence in the cosmos may have run exactly once, and we are it, and it can end. That is my warning, if you want to call it that. Not that the aliens are coming, not that we should fear what's out there. There's nothing out there to fear. The warning is that we are unspeakably rare, and we are behaving as if we are ordinary, as if there will always be another chance, another planet, another species to take our place. The physics says otherwise. The physics says this is it. Pay attention. Take care of it. I spent my life studying the laws of nature, and the more I learned, the more astonished I became that anything exists at all, let alone something that can understand the laws by which it exists. The universe didn't have to produce us. There is no law of physics that says matter must eventually become conscious. It just happened here, once. And that once is not a footnote. It is the whole story. We've looked and we keep looking, and the cosmos keeps answering with silence. You know, I've always believed that the purpose of science is to find out what's true, whether we like it or not, and sometimes the truth is uncomfortable. Sometimes the truth makes you feel lonely, but there is a deep satisfaction in knowing the truth, even when it's hard, because once you see things clearly, once you stop kidding yourself, you can begin to act wisely. You can begin to value what you actually have instead of fantasizing about what you wish were there. We live on a pale blue dot, a tiny world in an immense silent void. And on that world, for a brief flicker of cosmic time, matter has organized itself into beings that can love and argue and compose music and solve equations and wonder about the stars. Whether that flicker lasts another century or another million years is, in large part, up to us. No one else is going to make that decision. No one else even knows we're here. Maybe one day we'll hear something. Maybe there's a signal crossing the void right now, and we just haven't tuned to the right frequency yet. That would be wonderful. I'd love to be wrong about this. But until that day comes, the most honest thing a physicist can say is this: the universe is very, very large and very, very old and very, very silent. And the most likely explanation for that silence is the most straightforward one. No one else is talking. We're it. The whole show, the only audience and the only performers. So what are you going to do about it? If you found this perspective valuable, please hit like and consider subscribing to Winds of Thought for more explorations into the deep questions